Alright, here we go. So today, in this video, we're going to be discussing expected value. Now what expected value really means is just a long-term average, if you will. Okay. The idea is that over time, things are going to tend toward a certain value. Okay, so for instance, if you flipped a coin, let's say 100 times, how many heads would you expect to get? Well, you would expect 50 heads. And why would you expect 50 heads? Well, because it's a 50-50 chance. 50% of the time you're going to get them, so that's what you'd expect to get. What if there was no more than just two possible outcomes? What if there were more than just winning and losing? What if there was something different? For instance, suppose we rolled a dice. Now again, we're going to go back to the dice. I know I said I wasn't going to use dice that much, but you gotta do it sometimes. And if you wanted to keep track, obviously the probability that you get a 1 is 1 out of 6. 2, 3, 4, 5, and 6. So if you rolled the dice a bazillion times, it doesn't matter how many times right now, but if you rolled the dice a bunch of times and you added up the number of dots and you averaged the number of dots on each of those rolls, what would it come out to be? A lot of people would say, well, I don't know, 3 or 4 probably. You'd probably be pretty close. But here's what it is. We say the expected value, and we write it like this. Sometimes it's referred to as the expectation, but I like to call it the expected value, but your book refers to the expected value as well. But some books call it the expectation. And again, it's just a long-term average. What you do is that you take the sum, that's what this means. I goes from 1 to n. That means you're going to add up a bunch of things and take each of the x's times their probabilities. Okay? So in this situation, it's going to be 1 times 1/6 plus 2 times 1/6 plus 3, times 1/6 plus 4 plus 5 and plus 6 times 1/6. And when you do that, you will see that it comes out to be 21/6, which is 3.5. And over time, you would expect, if you added up, I got a 1 on this roll, and a 5, and a 4, and a 3, and a 1, and a 4, and a 5, and a 6, and a whatever. If you added them up over time, what you'd end up with is an average of about 3.5. That's what it should be. That's a theoretical average. Now, interestingly enough, I don't have enough dice to play. Now, I have better things to do than roll a dice, so I'm not going to roll a dice. I'm going to generate some of my own data. And what I'm going to do is I'm going to have the computer basically roll a dice for me. And so what I'm going to do is tell it that I'm rolling a dice, and so I'm going to generate the numbers 1, 2, 3, 4, 5, and 6. Like so. And those are their probabilities. Now it's 1/6. By the way, if you try to type it in as 0.1666667 like that, it won't work. So if you're playing along at home, like, I'm going to do this with you, I'm like, cool. You have to start off with 1 divided by 6 or it won't work. So data analysis. I don't have that. Well, don't worry right now. This is just for demonstration purposes. I'm going to roll one dice. I'm going to roll it 1,000 times. Sure. And this is how I'm going to decide what numbers to generate. And I'm going to put them in A1. Bam. Voila. There they are. Nice, huh? And so here it is. If you can scroll down here and check it out, there's 1,000 of them. You can trust me on that. It's true. Suppose I sum up that column, or average that column. I can just do the average of all of those rolls. .469. Friends, that's pretty darn close to 3.5. Now, is it ever going to be perfect? No, it's never going to be perfect. That's how life is. So in theory, it should be exactly 3.5. In this case, and the ones we just did here, it came out to be 3.469. The next one, it could be 3.52 or something, and 3.51 and 3.43, and all around there. It's not going to change a whole whale of a lot because that's where it's supposed to be, is right around there. It wouldn't be perfectly 3.5 even if you sat there and rolled a dice, with regular dice. It wouldn't be. But this is how we do it. This formula right here is how we find expected value. Now you're like, well, that's cool. Show me another example of that. Well, in Roulette, which is my favorite betting game, although I don't play games at all, but this would be my favorite one, I think, only because the math of it is so cool. Okay, and so if you've never seen a roulette wheel, and actually paid attention to it, the number's 1 to 18, the number's 19 to 36. Don't quote me on these. Every other, let's see. So there's 1 to 18. I'm sorry, 1 to 36. Okay, and half of those are black, and half are red. And then there's the number 0 and the number 00, and they are both green. Okay. Now you could bet on any number of cases, but let's say we're going to bet on any single number. Okay. Well, the probability of winning then is 1 out of 38. So if I were to make a table here, I would win, I'll just write win above it, 1 out of 38, and I would lose 37 out of 38, yes? In essence, right? And so the question, what do I win if I win? Well, turns out you win, for any single number, you will win $35 plus the $1 that you bet. So you'll actually win $36. That's what you will win right there. Okay. Well, what do you get if you lose? Well, you win nothing. So in other words, X is your winnings. Okay. So the expected value here, the expected value is the sum of, again, your X's times your P of X's. So in this case, it's going to be 36 times 1 out of 38. Plus 0 times 37 out of 38. Okay? But that's not all of this situation, because it costs you to play the game. So in the case of rolling the dice, I didn't charge you to play. We were just doing it, so the cost to play was 0. But in the case of this, I bet $1. So whatever happens, I have to remember to subtract $1 off of that. So 36 out of 38. This is 0, obviously. Minus 1 is negative 2 out of 38, which is about negative a nickel. So if you play this game over a long period of time, you would expect to lose a nickel per game. Okay? Now, think about that for a minute. How could I generate that? Well, I could come over to Excel, and I could actually do the same thing I just did here. Okay? But stop it. Give it to me. Here, escape. Yeah, but what I could do is actually go in here and go, all right, well, my probability of, I'll just put a 1 here. Actually, I'm not going to put a 1. I'm going to put a 36, because that's how much money I make. And a 0. That's handy. And that's 1. It equals 1 divided by 38. And equals 37 divided by 38. Right? And then what I can do is, again, go in here and I can generate some data and see what happens. So let's play the game. Heck, let's play it 2,000 times. By the way, that's $2,000 that I've bet. You with me on this? And here's where my values are going to go in. Voila, like so. And hit OK. Voila, there they are. And you lose. Oh, there's a win. Lose, win. Ooh, nice. But a whole pile of losses, man. So check this out. Suppose I took the sum of A1 to A2000. I made $2,196. That's awesome. But how much did it cost me to do that? Well, it turns out it cost me $2,000 to do this, which means I came out $196 to the good. But that's this much per game. In other words, I won basically on average 10 cents per game. That's kind of lousy. Now, what would have happened if I'd have won one less game? I would have only won 8 cents. Now, you're like, Jay, you got really lucky in there. Apparently I did. That's all I got to say, friends. Anyway, the point is you lose a few of those wins out of there, and it can really make a big difference, obviously. Okay? Now, and obviously this is a random generated scenario. So I could do another one. I'll do it maybe in this column. Now, obviously in real life this happens. Apparently we just found somebody's grandma here she's the gal who always goes to Vegas and always wins. By the way, good for your grandma. The rest of our grandmas go to Vegas and lose. Look at that. She won right off the bat. Yeah, this freaking lady. Anyway, equals the sum of D1 to D2000. This lady only won $17.28. And you're like, dude, she got smoked. Well, kinda. She came out behind. But how much is that per game? It looks like she lost 13 cents per game. And if you did this for everybody, this woman wins 10 cents, this woman loses 13 cents per game, and so on and so on and so on, and you average them up for all the people who play these games, it would average out to about a nickel a game you would lose when you bet on any single number. That's the long-term average. Okay? Now, you're a boring person. You're a person who's, I'm averse to risk. Don't make me do that one number business. I want to bet on odds. I want to win. I want to bet on odds on the wheel. Okay, well, there are 18 odds out of 38. Okay, cool. So that's the probability of winning if you bet on odds. Okay. Turns out if you bet on odds, you get $1 plus your dollar, you get $2. Yay! And if you don't win, you win, well, nothing. And so if you look at this, it's just 2 times 18 out of 38 plus 0 times 20 out of 38 minus $1. Son of a gun. It's 36 out of 38. It's negative a nickel again. And in fact, no matter what bet you make on roulette, the expected value is always the same. And this situation here, in the case of betting on odds, yeah, you're going to win more often, but you're not winning any money to speak of. You know what I'm saying? You win $1. Oh, I win a whole extra $1 than I bet. Whoop-de-doo. So no one really wants to probably do that as much. All right, it's just not something people get really that excited about. Oh, can I please bet on that? Other people go like, I'm going to swing for the bleachers. Good for you. Means you're going to lose more often, right? But when you win big. And you're like, oh, that's going to be better for me. Turns out it comes out the same in the long run. So here, I'm going to type in my, those are my values. And, oh yeah, D1 looks good to me. Voila. Boom, there they are. So if I do equals the sum of that column, D1 to D2000, I'll get 1926. And if I take that minus 2000, I will have lost $74, but that would make per game, I would have lost 3.7 cents per game on average. Again, that is what expected value means. Now, I don't know about you, but I'm not big on gambling. It's just not my thing. But somewhere where this does touch me is the idea of insurance. Okay? Insurance, how much they charge you, which is called the premium, right? That's what the company charges you. That premium is your cost to play. Okay? So whenever you take out insurance, you're betting that you're going to die, get sick, get in a car wreck. You know, someone's going to break into your house and cut themselves and then sue you, as you have to have the liability insurance. Who knows? So what they charge you is that called a premium, and it's what your cost to play the game is. Okay. Now I only look at this in this class level from a standpoint of life insurance and just term insurance. Okay? And so a person is going to die, let's say, if they take out a $100,000 life insurance policy, they win if they die. Okay? I win the money, yay, but you're dead. Say, did you really win? I don't know, okay? But you win this if you die. Well, fortunately, most of us don't have a really high probability of dying today. Maybe it's that, okay? So then I win nothing if I don't die today. So catch 22, I guess, right? And yeah, and so if you think about this, what the insurance company does is they look at it like this. So it's 100,000 times 0.00002 plus, of course, this times this is 0 minus the premium. And what the insurance company says is, look, we need to have a certain amount of profit per policy. Maybe it's $100 for this profit. Maybe it is for this one. I don't know. Okay? And so, listen, if for them it's $100 profit, for me that means I'm going to be $100 in the hole when it's all said and done. You with me on this? So my expected value is positive from the company. This is going to be negative. For the company, this will be negative, and this will be positive, and this will be positive for the company as well. Okay? But if they want to make $100, that means I have to lose the $100. I mean, it's got to come from somewhere. So what I'm going to do, it'd be nice if I had a real calculator. Let's go get a real one. Boop, boop. No, there you go. There we go. $2. So this is $2 plus 0 minus the premium needs to equal negative $100. In other words, the premium needs to be $102. Okay, that's what the company would have to charge you in order to make the $100 that they want to make per policy. Again, how do they do that? They figure that people that are your age, weight, smoking status, they don't jump out of airplanes, whatever it is, you have a certain probability of death. Okay, that's why they give you blood tests. That's why they do your, they send a nurse out to check you out before they insure you, because they don't want to have to be paying out $1 zillion when you kick the bucket tomorrow. They would like to be a situation where, yes, people die. People get in a car wreck. They can't. There's no accounting for that. People just they die. These things happen. You couldn't have foreseen it happening. But from a standpoint of, look, if you're this age and you have these factors, this is your probability of death. Because of that, we can feel good about charging you this premium so that you'll buy our policy. And yes, we're going to have to write some checks, but the rest of the time we're going to be bringing money in. Now, I have a lot of problems with the Affordable Care Act. I have a lot of problems with it. But from a math standpoint, you cannot argue the case that the idea that if you have more people paying in, the lower the younger people, that's what they want you to buy into it, the more people paying in, but that are not claiming money back out of it. So they're paying money in, the insurance companies get to sit on that money, but they end up having to pay it out on people who are more high risk. The idea being is that then they could then theoretically lower the prices on the higher risk people so that they could actually afford to get insurance. Okay? From a math standpoint, that makes perfect sense. From a bunch of other standpoints, I have problems with it. But that's that. Okay? That's how insurance always works in that regard. Okay? So clearly, if this thing goes up right here, right? If that goes up, that means this number here will go up. If this number has to stay the same, I want to make the same amount per policy, then the premium also then has to go up. So a friend of my dad's, really big guy, he's about 5'11". He's not big tall, he's big wide, probably 320 pounds back when this story took place. My dad sells life insurance, and he calls my dad up and he wants to buy a policy. Well, they're pretty close, but dad can just see it already happening. He's like, and he calls me, he's like, dude, they're gonna charge him like $1 million premium. And because he's overweight, he's diabetic, and he has this problem, that problem, the other thing, high blood pressure and whatever else. And well, it turns out he was such a high risk for dying that no company would even offer him a premium at any price. Because the probability that he keels over dead, it was so high that they would never, ever be able to recoup any money out of him, theoretically. Now, the guy is still alive. That was 10, 15 years ago. He's lost some weight, apparently. But the point is that obviously the more risk you are, the more likely the insurance companies have to pay out, the more they're going to have to charge you. That is why people who have pre-existing conditions get charged more, because they're more likely to have them again, obviously. That's why teenage drivers, boys especially, get charged more, because they're more likely to get involved in a wreck, and the company's going to have to pay out on them. Okay? That's where that comes from. It's all about the expected value. Okay? So that's that. It's pretty straightforward kind of a deal there in terms of that. It's just pretty easy deals in that regard there. Same thing could be said for a jackpot situation. Now your book shows some of these. Your book always writes them vertically, and I know why they do it. It just gets a little annoying. So they write it so it's in a vertical column. I prefer to look at it like this, but they'll have the jackpot, and it's like 1 in 175 million, 223, 510. Okay, when they say 1 in, what they really mean is 1 out of, like this. You see that? Okay, that's the probability of winning the jackpot. And then you can win $1 million. Okay, and the probability of that happening is 1 in 5,153,633, and so on and so on and so on. Okay, and it's pretty easy to do. Obviously, it's gonna, and there's more and more, and you could fill it in. But if you keep track of this jackpot, well, it's going to have to be different every time, right? So what if the jackpot was 10 million or 30 million or 40 million? So what I would suggest on a problem like that, because I got better things to do, is I would suggest using Excel. Now, by the way, as I mentioned previously, I had a student last term say that, quote, I cheated them out of doing math by using Excel. Still using Excel, just speeding the process up a little bit. Now, if I put in 30 million here, by the way, I'm going to make these all in the dollar sign so it's obvious that I've got it right. Maybe, there it is. And then I'm just going to go down the list here, so 1 million. Anyway, you are certainly welcome to use a calculator, use your slide rule, use your flip phone calculator. Hey, whatever works for you, man, whatever works for you. I think there's a typo. I think that's supposed to be 1,000. This is a problem number 31 in your text. I think there's a typo. There's 2 100s. That's just, well, there's 2 7s as well. That's odd. I don't really know what that's about. I'm not really sure what that's about at all. But whatever. Okay, I'll just go with it. And then here are the odds. So you're just going to do equals 1 divided by... Oop, no. Try again. Equals 1 divided by 175. 223. Oops. 510. 1 divided by 513. 5153. 633. You forgot the equal sign, you big dope. One divided by 648,976. Come on, dummy. Let's go. Equals. There you go. Try to do it right this time. 1 divided by 19,088 equals 1 divided by 12,245 equals 1 divided by 360 equals 1 divided by 706. Not really sure what those two being the same are all about. I'm not really sure, and I don't really care either. I'm just going to do the math. Okay, so what I could do over here, and again, this is something you could do by hand on your calculator. It's fine. I'm just going to do equals that times that, and then drag it down. That is probability expected. That is winnings times probabilities. Boom, and then I'm going to add them up. So I'm going to go to the sum of those values. That is the definition of expected value minus the cost to play. And it's a $1 ticket. So you would expect to lose 42 cents every time you played. Okay? So that's how that game is played. You're expecting to lose 42 cents every time you play a ticket. Now, if you make now that actually makes a lot of sense. Now, what if it was 10 million instead of 30 million? Okay? Well, think about that for a minute. Hey, I'm going to lose more money. How come? Because you have a less chance of winning on the top end of things. Now, again, it's one of those situations where they say, hey, you shouldn't expect to use it as an investment strategy. Well, duh. You're losing 53 cents every time you play. That's not a good way to make money. Now, again, some people get lucky and win. But remember, it's probably not going to be you. Just so you're aware of that. Now, you're always more than welcome to play, but that's how expected value goes.